Hello class, this is lesson 2.4. The topic is symmetry. So we will begin this lesson by discussing symmetry from a graphical point of view. That is, I will draw some graphs and discuss the types of symmetry. So let me start with the XY plane here. Okay, and I'm sure you sort of have a intuition of what symmetry is. It's when it looks the same on one side as it does on the other side. So let me draw a symmetric, ooh, that's not perfect here. Okay, so this is a symmetric graph. I didn't draw it perfect, but let's just pretend it's the same on this side as that side. So it's sort of like the y-axis here is acting like a mirror, and this stuff here is the mirror image of this stuff there. Right, so because the y-axis is acting like a mirror, we say this is symmetric about the y-axis. It's the language we will use. Okay? Now, let me draw a picture that is symmetric about the x-axis. So here, the x-axis will act like a mirror. So whatever happens on this side, the mirror image will happen on the other side. Okay, so it's sort of like this x-axis is a mirror. This is the mirror image of that. So this is symmetric about the x-axis. Okay, so these are pretty easy. There is one more type of symmetry I want to discuss. And that's when we're symmetric about this one point here, the point 0, 0, which we sometimes call the origin. So if that little point acts like a mirror, then whatever happens here, the mirror image will happen here. And I know my pictures aren't perfect, but let's pretend this was the mirror image of that. Okay, we call this symmetric about the origin. Okay, so this is the three types of symmetry we will be dealing with in this section. Either the y-axis is a mirror, the x-axis is a mirror, or this one point, the origin, is the mirror. And if you're already given the graph, these are pretty easy problems to answer, so I'm not going to do much more examples of this kind. So in your homework, if you're given a graph and you're asked what type of symmetry it is, basically asking you, is the y-axis the mirror, the x-axis the mirror, or is the origin the mirror? And it's also possible for a graph to not have any symmetry, right? So say we have, a graph like this, right? This one is not symmetric, right? And then we could also have yeah, so actually this is all the cases you will see. So we'll see this, this, or this case. And a few of your homework problems, you're just given graphs and asked to determine the type of symmetry it is. So that should be pretty easy. Okay, so this is the graphical way of doing it. Now I'm going to tell you the algebraic way of doing it. So we could start with y symmetry. Let me draw a graph that is symmetric about the y-axis. And this is y symmetric. Now let's make an observation here. Notice if we plug in some point here, call that point x. Okay, so if this is point x, well then if we flip over here to minus x, right, minus x will therefore be right here. And we can make the following observation, right? Notice how the outputs of both x and minus x, right, the outputs have the same y value. So that will always happen with y symmetry. See this y value corresponding to x and minus x, they both have the same y value. Right, so to determine if an equation is symmetric about the y-axis, we can do the following algebraic steps. We could replace all the x's in the equation with minus x, and then simplify. Okay, so after we do that, we could either have two things happen. If the simplified equation, or the simplified result, is the same as the original equation, right, that means we have y symmetry. It's symmetric about the y-axis. If the simplified result is different than the original equation, then all we can conclude is it is not symmetric about the y-axis. It is not y-symmetric. It may possibly be x or symmetric, but this test will just tell us whether or not it is symmetric about the y-axis. And looking at this graph, you could see why that is true. Replace the x with minus x, we should have the same outputs if it is in fact y-symmetric. Okay, so I'll just do an example. Consider the equation y equals x squared. Is this symmetric about the y-axis? Well, following the above steps, right, if we do step 1 here, we replace the x's with a minus x in the equation, and then we simplify. Simplifying, we get, well, a minus squared will just turn into positive, right? So this just turns into x squared because we squared the minus sign and it went away. And this is the same as the original equation. Thus, it is in fact symmetric about the y-axis. Okay, another example is y equals x cubed, symmetric about the y-axis. Well, if we replace the x with a minus x and then simplify, well, a negative sign cubed would still be negative, right? A triple negative is still negative. Now this equation is not the same as our original equation, and therefore we conclude y equals x cubed is not symmetric about the y-axis. Okay, moving on. For symmetry about the x-axis, we have the following picture. We have this graph here is symmetric about the x-axis. So notice if we plug in some number y and then the negative version of that y, then we would have the corresponding x value be the same. So to test for x symmetry, we replace all of the y's with minus y's and simplify. Okay, so now either two things can happen. Either the simplified result is the same as the original equation, if it's then the same as the original equation, right, then we give x symmetry. If it is different, then we just can conclude it is not symmetric about the x-axis. Okay, some examples. X equals y squared. Is this x symmetric? Well, we just take this equation and replace any y with a minus y, and then simplify. So if we square a minus sign, it goes away, and we're left with x equals minus y, which is x equals y squared, which is the original equation, and thus it is symmetric about the x-axis. Another example here is, let's say y equals x cubed, an example we already did. Let's ask ourselves, is this symmetric about the x-axis? Well, we just replace the y with a minus y and simplify if we can. There's nothing we can really do to simplify this, and it's clearly not the same as our starting point, so it's not x symmetric. Okay, now if you recall, there was one more type of symmetry that is symmetric about the origin. Okay, so let me draw a picture of a graph that is symmetric about the origin, and then let's investigate it. Well, here, if we plug in some number x, and then we plug in the negative version of the x, we don't get the same output. So if we plug in x, we will get some output y. But notice if we plug in minus x, we end up with minus y. So we have this type of symmetry, corresponding to x, some number y, corresponding to minus x, happens to be the minus y number. Okay, so how can we put this into a test? Well, let me show you how you can test this by looking at an example we've already tried twice. Let's look at y equals x cubed one more time. So notice we've tested y equals x cubed and found it was not y symmetric. We tested y equals x cubed and found it was not x symmetric. Let's look at it one more time and ask ourselves, is this symmetric about the origin. Okay. Well, we notice if we replace x with minus x, we get y equals minus x cubed. We simplify, we get negative x cubed, so triple negative is still negative. Right. Now, so now we could put the parenthesis here on the inside, right? So if you're kind of confused about that step, all I did was cube the negative 1 and realized negative 1 cubed is just negative. So I was allowed to pull the negative sign outside of the parenthesis. But notice that inside of the parenthesis is the original function, so right, so what did we figure out here? Well, that's how we figured out how we can do a test for symmetry about the origin. So let me just write this down for function f of x that is symmetric about the origin. We have the following result. If we plug in a minus x, we get the original function that we started with, but with a minus sign in front. So this is the test we can do for symmetry about the origin. And notice it worked. This passed the test here. We plugged in a minus x. We ended up with a minus sign in front of the original function here. So therefore we can conclude y equals x cubed is symmetric about the origin. Okay, now there's one last thing I want to discuss, and it's nothing new, it's just a new word to talk about symmetry. So if something is symmetric about the y-axis, so if something is y-symmetric, sometimes we use the word even function, right? So something that is symmetric about the y-axis we call an even function. And something that is symmetric about the origin origin symmetry is something we call an odd function. And the reason we use this language is it's sort of like how double negatives cancel out, or an even number of negatives will cancel out, and an odd number of negatives preserves the minus sign. So let me explain a little further what I mean by that. So for an even function f, right, we have that if we plug in a negative number, the negative just cancels out and we're left with what we started, which is exactly the test we were doing earlier. We just did not use the function notation. On the other hand, an odd function has the property I just barely mentioned. So for an odd function, say g of x, we get, when we plug in a minus sign, the minus sign is preserved. And that's sort of an extension of the idea that even many negatives cancel out, right? So for an even function, the negative you plug in will cancel out. For an odd function, the negative you plug in will be preserved. But really all an even function is what we just learned about. It's just y symmetry, and all an odd function is just origin symmetry. These are just new vocab words that you can use. Okay, so that is all for lesson 2.4. Thank you.